Next talk then, Jackson Shannon.
Thanks. You can go to the next slide. So hi everyone, my name is Jackson Shannon. I'm a mission design engineer at the Applied Physics Lab. So this is going to be more of a trajectory talk and mission concept, not so much focusing on the motivating science. But with that being said, at least so I've been told, low altitude neutron spectroscopy observations could help improve the spatial resolution mapping of the potentially viable near surface water ice resources at the moon's south pole. The challenge with that, at least from an orbital standpoint, is that there's an impact threat from high elevation terrain, as well as aspherical gravity perturbations that become very influential in low orbit. And so that poses a challenge for low altitude orbiters. Next slide. So we've been working on a ConOps to overcome these challenges, and the solution we're working right now involves dividing the lunar longitude space into two different regions, a terrain avoidance region and an observation region. The observation region is basically just a continuous set of longitudes that have very low threat for impact due to high altitude terrain. The terrain avoidance region is obviously the opposite, where we would need to raise our orbit or grow our orbit and to safely pass over high altitude terrain. So as the moon orbits the Earth in one lunar cycle, the moon would then rotate below our inertially fixed orbit, and it will basically allow the spacecraft to transition from one region to the next. And as it passes over some critical longitudes that we have marked here by red lines, we can then perform corrective maneuvers, either raising or lowering periapsis, either to perform low altitude observations or avoid a mountain that we might be flying right at. And so the great thing about this ConOp is that we're in the observation region in the low orbit for a limited amount of time, and so with the longitude ranges that are presented here, it's about 5 days, and so we have a limited amount of time for the aspherical gravity perturbations to have a large cumulative effect on our orbit, and so orbit degradation doesn't actually occur during that time period. And so these orbits are stable on the time frames that they're in each region. And by performing corrective maneuvers, we're effectively resetting our system each time we go from one region to the next. So this whole process can be repeated iteratively for longer mission durations. Next slide, please. So we've modeled this in high fidelity, put together a 2-month simulation to try to quantify the delta V that would be associated with this concept. And we're very pleased with the fact that it's overall it's very low, and so it's typically 3 to 5 meters per second per burn. So that's well within the existing propulsion capabilities for small spacecraft, and it's something that we could extend to many iterations, many cycles. Then we started to think about how we can actually place a spacecraft into an orbit this low. And we think that the best approach would be to basically copy what Lunar IceCube is doing. So leveraging a lunar rideshare opportunity, as well as a low energy trajectory and solar electric propulsion to basically chaotically capture at the moon and lower into our science orbit. Next slide, please. So just a quick concluding remark. So these low altitude orbits are achievable over the lunar south pole. Unfortunately, terrain avoidance maneuvers are critical, but luckily they're relatively cheap and they reduce our impact threat and allow us to extend our mission duration. Solar electric propulsion is absolutely going to be critical to deliver the spacecraft into our science orbits, but we do have those capabilities, and we're excited to say that we think that this mission concept would be achievable with a small spacecraft, either a large CubeSat or something like an ESPA class spacecraft, which is exciting. Thank you.
Thank you.